So if we were working in 3 dimensions, in R3, d equals 3, and then the measure of our domain, okay, our domain may in general be referred to as omega, okay, omega to the power 1 over d would be measure of omega to the power 1 over 3, and this would be a length, okay. So this is how we would extend this sort of idea to multiple dimensions. Okay, but then let's get back to our H1 functions. So V belongs to H1 on 0, comma L if the integral of the function square plus, now let me write it differently, measure of 0, comma L square v comma x square, the whole thing dx less than infinity. Okay, so we require that the function itself and its first derivative, squared and integrated, be bounded. And H1 there simply refers to the fact that we are attempting here to control not only the function itself, but also its first derivative. Right? If we go on and want to control also the second and higher order derivatives, then we would accordingly go to higher orders of H. Right? We'd go to H2, H3, and so on. Okay, so now you observe that when we say that UH belongs to SH, which where SH is equal to functions belonging to H1, when we say this, what we're saying is that UH is such that we expect that UH is such that the function itself be bounded, okay, because it is square integrable, the function itself, as well as its derivatives, okay. And as you can imagine now, we're saying something about the nature of the displacement field that we're expecting to find as our approximate solution. Okay, so what we're saying here is that UH and UH comma X are square integrable. Okay, let's look at functions that are H1. Okay. Okay, so examples. Okay, examples of H1 functions. Okay, so if we say V of x equals constant, no problem. Okay, if we say V of x equals sum k equals 0 to n a sub k x to the power k, okay, this is also all right. There is a third type of function that I want to consider, and I could write it out in the form that I've written out the first two functions here, but let me instead draw it. Okay, let me instead sketch it, because it will still convey the same idea, whereas defining it would require us to define things that we will need only later. Okay, so let me suppose that V is of the following form: linear, maybe quadratic, linear again, some other polynomial, linear again, constant. Okay? This sort of a function also belongs to H1. Okay? It belongs to H1 because clearly the function itself, if you square and integrate it, is bounded. At points such as this, you observe that v comma x, okay, is v comma x suffers a jump. Okay, those double brackets there indicate a jump in a function. Okay, we know that there is a jump in the function there because if we look at the derivatives, right, we know that the derivatives are going to look like that. Right? The derivatives are going to be essentially the tangent to the two sides of the curve, right? Those tangents are not the same, right? And therefore we know that the function itself suffers a jump. However, discontinuous functions can still be squared and integrated. Okay, in fact, we considered exactly such a case in the case of L2 functions, right? We did consider it the discontinuous function itself, the Heaviside function, and observed that yes, it belongs to L2. So Heaviside functions, discontinuous functions can be squared and integrated. That's what happens with v comma x when it comes to defining it to be in H1. Okay, right? However, what about a function which has this form? Right, let's do something that looks pretty much like what we have there. What about this function? Right? As we saw in the case above, we see that yes, here the tangents are different, right? So there is a jump in v comma x. But out here, what we are seeing is that v itself suffers a jump. Okay, and therefore what happens when we consider v comma x? V comma x, we know, goes as a delta function. So if we call this point x naught, right, we know that v comma x is like a delta of x minus x naught. Okay, and that's where the square integrability of the derivative of v breaks down. Okay, so in this case we have v does not belong to H1. Okay. All right. This is probably a good place to end this segment. We've essentially gone over the definition of our very basic function spaces, introduced these ideas that we need here, ideas of square integrability of the functions and of their derivatives, and this idea that when we specify these functions to belong to certain spaces, these Hilbert spaces, L2 and H1, by the way, are Hilbert spaces, we gain control over the functions themselves and over their derivatives.